electricity.
Voltage is the pressure that makes it go. It's pushing up.
Electricity, electricity.
Watts will tell you just how much you'll be using up.
Electricity, electricity.
The electron transfer theory is the concept of redox reactions that applies to the galvanic cell, or more specifically, the Daniell cell. The oxidation half reaction occurs in the anode of the Daniell cell, while the reduction half reaction takes place in the cathode. When an external circuit, such as metal wire, connects the electrodes, the redox reaction takes place in the Daniell cell. The cathode contains the positively charged pole of the battery, where it accepts electrons from the external circuit. Copper metal is deposited on the cathode, and zinc becomes a part of the aqueous solution. This cathode contains the highest electrode potential. The anode is the negatively charged pole of the battery, where zinc provides electrons to the external circuit. This is the half cell containing the lowest electrode potential. Faraday's laws are the relationship between electricity and electrochemical changes. Michael Faraday's study of electrolysis identified the factors that determine the mass of an element produced or consumed at an electrode. The first law states that the amount of electricity used at an electrode is relative to the quantity of chemical change produced by a current. The second law states that different substances with the same amount of electricity produce quantities of chemical changes that are relative to their equivalent weights. The Faraday constant equals to 9.65 times 10 to the exponent 4 C per mole. This concept can be applied to an electrolytic cell in order to relate the mass of the metal deposited to the quantity of electricity used. For example, when changing a Daniell cell to an electrolytic cell, 0.1 moles of zinc needs to be placed onto the zinc electrode. A stoichiometric relationship is shown by the coefficients of the reduction half reaction of zinc. According to this table, the half reaction shows that for every mole of zinc deposited, 2 moles of electrons are required. Thus, 0.2 moles of electrons are used to deposit 0.1 moles of zinc. The lead-acid battery is a secondary battery which is rechargeable. It is used in automobiles containing 6 2V cells connected in series. The cathode is a positive plate of lead grids filled with lead 4 oxide. The anode is a negative plate containing lead grids filled with spongy lead. The electrolyte is aqueous sulfuric acid. The current output is increased by the use of grids because the electrodes are cells connected in parallel, anode to anode and cathode to cathode. The cell potential of the oxidation reaction is 0.36 volts. The cell potential of the reduction half reaction is 1.68 volts. Therefore, the cell potential of the redox reaction is 2.04 volts. This shows that the redox reaction taking place is spontaneous when discharging. In order for the cells to recharge, the reaction is reversed and becomes non-spontaneous. This is a representation of how a rechargeable battery works. During the discharging process, electrons from the anode are transferred to the cathode. When the battery is being charged, the electrons move from the cathode back to the anode and become negatively charged. This cell can discharge and recharge many times until it is diminished.
Overpotential or overvoltage
is the extra potential for a battery to make it go. The overall potential is a summation of many individual losses. Voltage efficiency describes that energy lost through overpotential. In electrolytic cell, the overpotential requires more energy than thermodynamically expected to drive a reaction. In galvanic cell, it means less energy is recovered than thermodynamics would predict. In each case, the extra or missing energy is lost or gained as heat. There are two types of electrolytes. The first one is strong electrolytes. They are almost completely ionized when dissolved in a polar medium like water. The most typical electrolyte is an ionic solution, but molten electrolyte and solid electrolytes are also possible. They are excellent conductors in solution. Their degree of ionization is very high. Some examples are nitric acid, hydrochloride, potassium hydroxide, and sodium hydroxide. The second type of electrolytes is the weak electrolytes. They are not completely ionized when dissolved in a polar solvent. They are poor conductors of electricity, and their degree of ionization is much less. Equilibrium between ions and unionized molecules established in solution. Some examples of weak electrolytes are acetic acid, phosphoric acid, boric acid, and ammonium hydroxide. In each type of battery, there are different elements in them. An example would be mercury oxide. In this type of battery, pure mercuric oxide or a mix of mercuric oxide with manganese dioxide are used as the cathode. Sodium hydroxide or potassium hydroxide are usually used as the electrolyte. The reduction reaction would be mercuric oxide to mercury, and oxidation reaction would be zinc to zinc oxide. The standard electrode potential would be 1.559 as calculated. The pros of this battery is the constant voltage and lasts up to 10 years, whereas the cons of this battery would be the high drainage, and it is a serious health concern. Therefore, a lot of countries have stopped producing them. Another example of battery is silver oxide. It is a small-sized primary battery. Its electrolyte usually is an alkaline electrolyte, such as sodium hydroxide and potassium hydroxide. The reduction reaction is silver oxide to silver, and oxidation reaction is zinc to zinc oxide. The standard electrode potential is 1.562 joules. The advantage of this battery, it is used in commercial button cell, such as in the watch or hearing aid, and the voltage is maintained. The cons is very expensive. Why so? Because silver is expensive. The last type of battery with different elements that I will talk about is alkaline battery. It is usually used with zinc and manganese dioxide. The electrolyte is potassium hydroxide. The oxidation reaction is zinc solid to zinc oxide solid, whereas reduction reaction would be manganese dioxide solid to manganese oxide solid. The standard electrode potential is 1.986 joules. It's the highest out of all the other two batteries. Some advantages are economical, reliable, high energy density, and long shelf life. Some disadvantages would be the tendency to leak, which causes corrosion and damages, and the voltage seems to decrease over time.